All right, let's get right into it. We're about to go on a journey that stretches across hundreds of millions of years. Seriously, we're going from the bottom of ancient oceans all the way to the engine in your car. This is the incredible, complex story of fossil fuels, what they are, how we got so good at using them, and the massive impact they have on our world.
It's a pretty wild thought, isn't it? The very energy that powers our modern world, our cars, our electricity, everything, it all started with this. Just tiny little plants and microscopic animals dying, sinking to the bottom of the sea and kicking off a process that would one day fuel, well, our entire civilization. So, what exactly are we talking about when we say fossil fuels? You can think of them as basically ancient life that's been buried, squashed, and cooked for an eternity. Whether we're talking about solid coal, liquid petroleum, or natural gas, they all share one critical ingredient: hydrocarbons. These are molecules made of hydrogen and carbon, and they are packed with chemical energy. And let me tell you, this process is anything but fast. We're talking geological time. As millions of years go by, more and more layers of sand and rock pile on top. This creates this incredible pressure cooker deep underground. That heat and pressure slowly bake the ancient organic stuff, transforming it into the energy-packed fuels we're so eager to find today. Okay, so pulling that black goo, crude oil, out of the ground is just step one. In its raw form, it's not actually all that useful. To really unlock its power, we have to send it to a refinery for a massive industrial makeover. And this is the heart of the whole operation, the fractionating tower. You can think of it like a giant sorting machine for molecules. See, crude oil is just a big, messy mixture of all sorts of different hydrocarbons, and this tower's job is to neatly separate that mess into useful groups, or what the industry calls fractions. Now, the science behind it, called fractional distillation, sounds complicated, but the idea is actually pretty straightforward. First, you heat the crude oil so hot that it turns into a gas. This hot vapor starts rising up the tower. Now, the tower is coolest at the top and hottest at the bottom. So as the vapors rise, they cool down and turn back into liquid at different levels. The really heavy, long molecules condense lower down, while the lighter, smaller ones keep rising way up high before they condense. And this is where it all connects back to you and me. Those different fractions, collected at different heights, become the things we use every single day. Up at the very top, the lightest gases become LPG for cooking. A bit lower, you get petrol for your car, then kerosene for jet fuel, and way down at the hot bottom, you get the heavy stuff, like diesel oil and that super thick, sticky bitumen we use to pave our roads. So here's the key takeaway. A hydrocarbon's personality all comes down to its size. Small molecules, like the ones in petrol, have weaker bonds holding them together. That's why they boil at low temperatures, flow super easily, and evaporate in a flash. But the big, long-chain molecules, like bitumen, they've got much stronger forces, which makes them thick, gooey, and you have to get them really hot to boil. And that same size difference totally changes how they burn. Those little hydrocarbons in petrol are super flammable. They mix with air really well and burn with a nice, clean flame. The big, heavy molecules in something like bitumen, they're much harder to get burning, and when they do, they tend to produce a lot of soot and smoke because they just don't burn as completely. Okay, so we've figured out how we get these fuels, but now we have to talk about what happens when we actually use them. Because the very chemical reaction that makes fossil fuels so amazing is a double-edged sword, and it comes with a pretty big price tag. This is why we go through all that trouble. Burning hydrocarbons is what's called an exothermic reaction. All that means is that it releases energy. In this case, a huge amount of heat energy. It's this blast of heat that we harness to do everything from pushing the pistons in an engine to boiling water to spin turbines in a power plant. It's the engine of the modern world. But here's the price. That powerful reaction is almost never perfect. It creates a whole cocktail of nasty byproducts. If it doesn't burn completely, you get poisonous carbon monoxide. The insane heat inside an engine actually cooks the air itself, creating nitrogen oxides. Then you've got impurities in the fuel that release sulfur dioxide, and tiny particles of soot get thrown into the air. These aren't just abstract chemicals. They're real pollutants with serious consequences for our health. And the story doesn't end there. The impact of all these pollutants doesn't just stay where we can see it as smog. When they get into the atmosphere, the problem scales up from a local issue to a global one. One of the first huge global problems we noticed was acid rain. Remember that sulfur dioxide and those nitrogen oxides? Well, when they get up into the clouds, they mix with water and form acids. This acidic water then falls back down as rain. And it's no joke. It can damage huge forests, poison lakes so fish can't survive, and even physically eat away at stone buildings.
But there's an even bigger effect happening. You see, our atmosphere naturally works kind of like the glass roof of a greenhouse. It lets the sun's light and heat in, but it traps some of that heat from escaping back into space. This natural greenhouse effect is actually a good thing. It's what keeps our planet warm and livable.
The problem is we've been making that glass roof thicker. The main thing you get from burning fossil fuels perfectly is carbon dioxide, or CO2. By pumping billions of tons of extra CO2 and other gases into the air, we're beefing up that greenhouse effect. We're trapping more and more heat, and that's causing the planet's average temperature to rise. And look, this isn't just a guess. The data is crystal clear. This chart shows the actual, measured rise in global temperatures ever since the Industrial Revolution got started, which is exactly when our fossil fuel use exploded. That trend line is undeniable. It's going up. That's global warming. And a warmer planet isn't just a number on a page. It has real-world effects that we're already starting to see. We're talking about massive ice caps melting at the poles, which causes sea levels to rise. We're talking about more frequent and more intense weather events all over the globe. So, faced with all these issues, we've put a lot of brainpower into trying to clean up our act. The big question is, can technology help us reduce some of this harm? One of the smartest pieces of tech we've come up with is the catalytic converter in your car. Think of it as a little chemistry lab in your exhaust pipe. As the toxic exhaust gases pass through it, precious metals like platinum trigger a reaction that turns the worst pollutants into much less harmful stuff, like plain old nitrogen gas and CO2. On a much, much bigger scale, you have things like industrial scrubbers in giant power plants. The basic idea here is to wash the waste gases before they leave the smokestack. They spray a chemical mist that reacts with pollutants like sulfur dioxide and captures them, preventing them from ever getting into the atmosphere to cause acid rain. But even with all this clever technology to burn fuels more cleanly, we run headfirst into another, much bigger problem. This quote really says it all. These resources, the ones that took millions and millions of years to form, are limited. There's only so much of it in the ground, and we are burning through it at a staggering pace. Which leaves us with this one massive question. Fossil fuels are really just ancient buried sunshine, a huge battery of solar energy stored over eons. We built our entire modern world on this incredible energy source. So what happens to that world when the battery finally runs out?